Hello dear students, welcome back to the next session of classification of elements. In the last session, classification of elements based on SPDF blocks and periodic properties, atomic radius, ionic radius, isoelectronic series completed. Now let us discuss the ionization potential. So what is meant by ionization potential? Here ionization, that means which converted into ion. Potential means what? Energy. So generally, a neutral atom is converted to ion. Neutral atom is converted to ion. For this purpose, we require some amount of energy. That energy is known as ionization potential. So, what is the definition of ionization potential? The minimum amount of energy. The minimum amount of energy required to remove an electron from the outermost shell of gaseous isolated neutral atom. The minimum amount of energy required to remove an electron from the outermost shell of gaseous isolated neutral atom is known as ionization potential. Right? See, let us consider it is a neutral atom M. To remove an electron from its valence shell, that is converted as M plus ion and releases one electron. Here this is gaseous neutral atom. Here this is uni-positive ion converted as a uni-positive ion. This is also gaseous state, right? Neutral atom converted to uni-positive ion. It requires some amount of energy. That energy is known as first ionization energy. That means from the neutral atom we remove an electron. We require some amount of energy. That energy is known as first ionization energy. Now I want to remove the one more electron from the uni-positive ion. That means M plus. This is a uni-positive ion. Uni-positive ion requires some energy IE2, that it is converted as a M plus 2. To remove the one more electron from the uni-positive ion, we require some energy. That energy is known as second ionization energy. Second ionization energy, and this is known as a di-positive ion. Di-positive ion. Similarly, I want to remove the one more electron from the di-positive ion, requires some energy, that is known as third ionization energy. Fourth ionization energy, one more electron, like this. That means here IE1, first ionization energy is less than IE2, less than here IE3, IE4, and so on, IEN. That means second ionization energy is always greater than first ionization energy. Second ionization energy always greater than first ionization energy, and third ionization energy always greater than second ionization energy. Right? See, IE2 is always greater than IE1. The reason is that in neutral atom, equal number of electrons and protons are present. To remove the electron is requires less amount of energy. Neutral atom converted to monopositive or unipositive ion. To remove the one more electron from the unipositive ion, converted to dipositive ion requires some more amount of energy. Why? Because here in unipositive ion, the number of electrons are decreases and effective nuclear charge increases. With that, the electrons are strongly attracted towards the nucleus. That's why to remove the electron from the unipositive ion requires high amount of energy. Second ionization energy requires more energy than first ionization energy. Second ionization energy or ionization potential always greater than first ionization potential. Is it clear? In neutral atom, equal number of electrons and protons are present, whereas in unipositive ion, electron number is decreases and effective nuclear charge increases. Right? Now units: electron volt per atom, kilocalorie per mole, kilocalorie per mole or joule per atom or kilojoule per mole. Here ionization potential means energy. That means energy can be units having electron volt per atom or joule per atom or kilocalorie per mole or kilojoule per mole. 1 electron volt equal to 23.06 kilocalorie per mole or 94.56 kilojoule per mole or 1.602 into 10 power minus 19 joule. 10 power minus 19, 1.602 into 10 power minus 19 joule per atom. Joule per atom, right? Here joule per atom. So these are the units of ionization potential. Units of ionization potential, right? Next, what are the factors influence on ionization potential? What are the factors influence on ionization potential? See, first one is factors influence on ionization potential. Factors influence on IPR, IE. First one is atomic radius. Atomic radius. As increase the atomic radius, ionization potential decreases. Ionization potential decreases. See here, let us consider the lithium. Now, let us consider it is a 1, 2, 3, 4, 5. See, lithium, sodium, potassium, rubidium, cesium. Lithium 1s2s1, sodium 1s2 2s2 2p6 3s1, potassium 4s1, rubidium 5s1, cesium 6s1. That is 1, 2, 3, 4, 5. So one more shell. See here small atomic radius. Here large atomic radius. So down the group what happen? Atomic radius increases. When atomic radius increases, here let us imagine one electron is present in the valence shell. Here also one electron is present in the valence shell. To remove the electron, here lithium or small size of atom requires more energy or large size of atom requires more energy. See small size of atom, here the distance is less from the nucleus over the valence shell of electron. Atomic radius is less. That means the electrons are strongly attracted towards nucleus. Here the large distance from the nucleus over the valence shell of electron. Here nucleus force of attraction is less. That's why we can easily remove the electron. We can easily remove the electron means it requires more energy or less energy. We can easily remove the electron. That means it requires less energy. Down the group, as increase the atomic radius, ionization potential decreases. Right? Down the group, see, down the group, atomic radius, what happened? Increases. When atomic radius is increases, ionization potential what happened? IP. Down the group, atomic radius increases. There is a large distance, less nucleus force of attraction over the valence shell of electron. Why? Because more number of shells, a large distance between the nucleus and valence shell of electron. So it requires less energy. We can easily remove the electron, but here it is very difficult. That means strongly attracted towards the nucleus because of small size. See, atomic radius down the group increases. Then ionization potential down the group what happen? Ionization potential down the group decreases. Is it clear? IP down the group decreases due to increasing the atomic radius. Now in periods, see in periods, along the period from left to right, atomic radius decreases. And so atomic radius decreases means to remove an electron requires high amount of energy. Left to right along the period, for example, see lithium, beryllium, boron, nitrogen, oxygen, fluorine, neon. Left to right, what happened? Atomic radius decreases. Small atomic radius, if the electrons are strongly attracted towards the nucleus, to remove the electron requires high amount of energy. That means along the period, ionization potential increases due to decrease in atomic radius. Right? Yes, we can represent like this one. Ionization potential property. Down the group, what happened? Decreases. Whereas left to right increases. What is the reason behind it? The reason is due to here down the group decrease means atomic radius increases. Left to right ionization potential increase means what is the reason? The reason is atomic radius is decreases. Hence ionization potential increases. Right? Next. So students, next one is factors influence on ionization potential. Factors influence on ionization potential. IP means ionization potential. The first one is atomic radius or atomic size. Atomic radius. Atomic radius. See, atomic radius is inversely proportional to ionization potential. Right? As increasing atomic radius, ionization potential decreases. Right? Second one is nuclear charge. Nuclear charge is directly proportional to ionization potential. More the nuclear charge, more the ionization potential. Why? Because the electrons are strongly attracted towards nucleus. Hence, it requires high amount of energy. Third one is screening or shielding effect. Screening or shielding effect. So, what is a screening or shielding effect? Let us see. So, generally, we know that the valence shell is a last shell, and before the valence shell is penultimate shell. The inner shell of electrons prevent the nucleus force of attraction towards the valence shell of electron. This phenomenon is known as screening or shielding effect. That means the electrons are prevent the nucleus force of attraction from the nucleus or the valence shell of electron. They act as a screen. Hence, it is known as screening effect or shielding effect. Let us see. Nucleus, here the atom, different shells are present. Let us imagine it is a valence shell, here electrons are present. This is the inner shell of electron or penultimate shell of electron. The nucleus force of attraction initially fall on these inner shell of electron. This shell prevent the nucleus force of attraction over the valence shell of electron. ఈ బిఫోర్ షెల్లో ఉన్న ఎలక్ట్రాన్స్ ఈ న్యూక్లియస్ ఫోర్స్ ఆఫ్ అట్రాక్షన్ అనేది నేరుగా చివర ఉన్నటువంటి వ్యాలెన్స్ షెల్లో ఉన్న ఎలక్ట్రాన్లపై పడకుండా ఇవి ప్రివెంట్ చేస్తున్నాయి. కాబట్టి న్యూక్లియస్ ఫోర్స్ ఆఫ్ అట్రాక్షన్ ఈ వ్యాలెన్స్ షెల్లో ఉన్న ఎలక్ట్రాన్లపై ఎక్కువగా ఉండదు. కాబట్టి ఎలక్ట్రాన్ మనం ఈజీగా రిమూవ్ చేయవచ్చు. ఎలక్ట్రాన్ ఈజీగా రిమూవ్ చేయవచ్చు అంటే ఎక్కువ ఎనర్జీ అవసరం అవుతుందా, తక్కువ ఎనర్జీ అవసరం అవుతుందా? తక్కువ ఎనర్జీ అవసరం అవుతుంది. దట్ మీన్స్ స్క్రీనింగ్ ఎఫెక్ట్ ఆర్ షీల్డింగ్ ఎఫెక్ట్ ఎక్కువగా ఉందనుకోండి, ionization potential తక్కువగా ఉంటుంది. Here screening effect is inversely proportional to ionization potential. Is it clear? So what is the screening effect? The inner shell of electrons in an atom prevent the nucleus force of attraction over the valence shell of electrons. This phenomenon is known as screening or shielding effect. Right? So based on this screening or shielding effect, generally in transition elements, the decrease in size, atomic radius decreases slightly. What is the reason? Due to the poor screening or shielding effect. Similarly, in lanthanides also, the atomic radius is slightly decreases due to poor screening or shielding effect. This decrease in size of lanthanides is known as lanthanide contraction. Similarly, in actinides also, here the actinide contraction, right? Screening or shielding effect is inversely proportional to ionization potential. The next one is half filled or completely filled. Half filled or completely filled electronic configuration. Half filled or completely filled electronic configuration. See, nitrogen, oxygen, one is to configuration of nitrogen 1s2, 2s2 and 2p3, right? Here this is 2s2 and this is 1s2. Is it clear? 1s2, 2s2, 2p3. This is 2p3. Here in 2p3, each orbital filled with one electron. This is a half filled electronic configuration. So half filled electronic configuration is considered to be highly stable. To remove the electron from the half filled electronic configuration requires more energy than oxygen. Here oxygen 1s2, 2s2, 2p4. Here 2 electrons, 2s2, 2 electrons, but in 2p4, 1, 2, 3, 4. Remember, nitrogen has ionization energy, IE1 is greater than oxygen. IE1, ionization energy, first ionization energy of nitrogen is greater than oxygen. Why? Because due to half filled electronic configuration. Similarly, beryllium, boron, which has more ionization potential. Beryllium, boron, which has more ionization potential. Beryllium has more ionization potential. Why? Because it is completely filled electronic configuration. 1s2, 2s2, completely filled electrons. Whereas in case of boron, 1s2, 2s2, 2p1. Here not completely filled, not half filled. So beryllium has more ionization energy than boron. Beryllium IE1 is greater than boron. Is it clear? IE1 of beryllium is more because completely filled electrons and s orbitals are closely towards nucleus, more penetrated towards nucleus. Right? The next one is penetration of SPDF orbitals. Penetration of SPDF orbitals, let us see here. Penetration of SPDF orbital, fifth one. Otherwise, see the next one. See, next one is penetration of SPDF orbitals. Penetration of SPDF orbitals. Generally, S orbitals are more penetrated towards nucleus than P, than D and F. Penetration order. Penetration order. S orbitals are spherical in shape. P orbitals are dumbbell, double dumbbell, fourfold dumbbell. These are closely towards the nucleus, more penetrated towards nucleus. That's why to remove electron from S orbital is requires high amount of energy, right? So this is penetration of SPDF orbitals. See, ionization energy of IE1 of second period. IE1 of second period elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Right? See, lithium 1s2 2s1. Beryllium has paired electron 1s2 2s2. Boron and carbon, nitrogen has half filled electronic configuration. That's why more ionization potential. Oxygen, fluorine and neon. That means second period, the more ionization potential is neon. Why? Because it is octet configuration. Least ionization potential is, first ionization potential is lithium. Is it clear? That means 1s2 2s1. Here 1s2 2s2 paired electron. Here also 1s2 2s2 2p3 half filled. Half filled electrons, half filled electronic configuration. Here paired electrons, completely filled electronic configuration. Completely filled electronic configuration. Right? Next, IE2. IE2 of second period. What is the meaning of IE2 of second period? IE2 of second period means to remove the one more electron from the unipositive ion, right? For example, lithium, from this one more electron. Lithium has more ionization potential than beryllium. Here boron 1s2 2s2 2p1. And the boron has more ionization potential than carbon, nitrogen. Here oxygen has more ionization potential, fluorine and neon. Is it clear? Ionization energy IE2 second ionization energy. That means just should remove the one electron. One electron means only 1s2. To remove the 1s2, one electron from the paired electron, it requires more amount of energy. It requires more amount of energy. That's why second ionization energy, lithium greater, next beryllium, here the boron greater, carbon, nitrogen, here oxygen has more second ionization energy. This is first ionization energy order. First ionization energy order. This is second ionization energy order. Right? And remember the highest ionization potential is helium, least IP ionization potential containing element is cesium. Highest ionization potential is helium. Least ionization potential is cesium. Right? Because large atomic size, hence we can easily remove the electron from the valence shell. Right? Next. See students, here the next one is ionization potential order for third period of elements. Ionization potential, ionization energy of third period. Third period elements. See, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. See the IE1 of sodium. Here the remove the one electron, requires less amount of energy. Here the more energy. Aluminium 1s2, 2s2, 2p6, 3s2, 3p1, less energy. Silicon, here the phosphorus requires more energy. Why? Because half filled electronic configuration. Sulfur, next chlorine. Next IE2. Here sodium requires more. Next magnesium less. Here aluminium greater. Silicon less. Phosphorus. Here sulfur greater. Chlorine and then argon. Right? In third period, second ionization potential order. This is first ionization potential order. Right? Next, successive ionization potential. Successive ionization potential. So, what is the successive ionization potential? So, based on the successive ionization potential, we can find the number of the valency of an atom. Valency, we can find the valency of an element. Successive ionization potential means here the ionization energy, when we remove the electron, some amount of energy required. Now, here the successive ionization potential means there is sudden jump to remove the electron. The energy difference is sudden jump. That is known as successive ionization potential. See here, with successive ionization potential, we can find the valency of an element. The successive ionization potential, here the successive ionization potential means sudden jump. Remember, sudden jump or large difference between ionization potential. See, the successive ionization enthalpy of an element M. The successive ionization enthalpies are given here: 5.98, 18.8, 28.44, 119.96, 153.77 electron volt per atom. So, what is the formula of chloride? See, based on this, here the first ionization potential, imagine, that is to remove the one electron, 5.98 electron volt per atom energy is required. Next, second electron, 18.8. Third electron, to remove third electron, 28.44. From third electron to fourth, that means I3 to I4, there is a sudden change. Sudden change. That means the atom can easily lose 3 electrons. After losing 3 electrons, it is considered to be highly stable. Why? Because here the energy difference 28.44 to 119.96. That means the formula of the chloride of M can lose 3 electrons. So valence is 3. That means 3 electrons can easily remove. It requires less amount of energy. But to remove the 4th electron, it requires high amount of energy. That means I3 to I4 it requires high amount of energy. That means the valency of the chloride of M is M. The formula is MCl3. Is it clear? Right? This is successive ionization enthalpy. Right? Is it clear? Successive ionization potential means here the sudden jump in the ionization potential to remove the electron. Here the 5.98, 18.8, 28.4 from third to fourth ionization potential. That means it requires here the high energy. So it loses 3 electrons easily. That means valence is 3. Right? Next. See, next one is electron affinity. Electron affinity. Electron gain enthalpy or electron affinity, EA. So what is meant by electron affinity or electron gain enthalpy? See, electron means electron gain, accepting, enthalpy means energy. To the neutral atom, when we add one electron to the isolated gaseous neutral atom, the atom accepts that electron, takes that electron and release some amount of energy. That energy is known as electron gain enthalpy. Electron gain enthalpy. When an electron is added to the neutral atom, see, neutral atom added one electron, it takes the electron and converted as a negative ion and releases some energy. This is known as first electron affinity or first electron gain enthalpy. Now to this uni negative ion, if we add one more electron, M minus 2, here energy also released. But here this EA1, first electron affinity, this is EA2. Right? See, EA1 is always exothermic, EA2 is endothermic. Exothermic means amount of energy released. Endothermic means amount of energy absorbed. See, to the gaseous neutral atom, we add one electron. It takes the electron, release some amount of energy, converted as a negative ion, uni negative ion. To this negative ion, add one more electron. Here, the di-negative ion is formed. This is known as second electron affinity. Some amount of energy released, that is second electron affinity. Remember, electron affinity EA1 is always, first electron affinity is always exothermic, second electron affinity is endothermic, because due to number 1, inner electronic repulsions, and second one is small atomic atomic size, small atomic size or atomic radius. Due to small atomic size and inner electronic repulsions, second electron affinity is always endothermic. Second electron affinity is endothermic, right? Is it clear? See, units of electron affinity, units, electron volt per atom, kilojoule per mole or kilocalorie per mole, kilojoule per atom or kilocalorie per mole, kilocalorie per mole. See, for noble gases, electron affinity is 0, considered to be 0. Why? Because these are octet configuration, highly stable, octet electronic configuration, highly stable, right? Highly stable. Second electron affinity is always positive. That means endothermic reaction. Endothermic, that means amount of energy absorbed. What is the reason behind it? Is the reason is inner electronic repulsions and small atomic size. For example, if the atom having small atomic radius, to add one more electron, there is a repulsion between the newly coming electron and already present electrons. That is inner electronic repulsions. That's why second electron affinity, the energy released, but released energy is utilized. That means absorbed. Here, electron affinity is always exothermic except beryllium, nitrogen, right? Beryllium, nitrogen, because it is a completely filled, it is a half filled electronic configuration. For these Be and N, electron affinity, first electron affinity is endothermic. Generally, first electron affinity is always exothermic except beryllium, nitrogen. Okay, except beryllium and nitrogen, first electron affinity is always negative, right? Whereas second electron affinity is endothermic. Second electron affinity is endothermic, right? To overcome the repulsions, the energy is utilized, right? That is the reason why second electron affinity is positive. Beryllium, nitrogen, and another one is magnesium. This is completely filled, half filled. For these beryllium, nitrogen, magnesium, first electron affinity is positive. That means endothermic. Remember, except EA1 is always exothermic except beryllium, magnesium, and nitrogen. Whereas EA2 is endothermic due to inner electronic repulsions and small atomic size. See, fluorine, chlorine. Among these two, chlorine has more electron affinity than fluorine. Why? Because fluorine has small atomic radius and inner electronic repulsions takes place. That's why chlorine has more electron affinity than fluorine, right? Okay. Next, variation of electron gain enthalpy in groups and periods. Variation of electron affinity in groups. In groups, what happened? Down the group, atomic radius increases. As increase the atomic radius, electron affinity decreases. Why? Because to add electron, less amount of energy released. Down the group, electron affinity decreases, whereas along the period, in periods, what happens? Electron affinity increases due to small atomic radius. Due to small atomic radius. Due to increase in atomic radius. Right? See, fluorine, chlorine, bromine, iodine. Down the group, atomic radius increases. Electron affinity decreases. That means fluorine, actually the variation of electron affinity. Normally down the group electron affinity decreases, but here fluorine has a less electron affinity than chlorine. Why? Because due to small size of fluorine atom and inner electronic repulsions. Chlorine has more electron affinity. Chlorine has more electron affinity than fluorine. Right? Highest electron affinity containing element is chlorine. See here, right? Highest electron affinity containing element is chlorine. Next, see students, here the electron affinity of see 50A nitrogen, phosphorus, in 60A oxygen, sulfur, in 70A fluorine, chlorine, whereas in 50A, 60A, 70A. Second element more En than first elements. Right? Electron, sorry, Ea, not En. Second element more electron affinity than first element. More electron affinity than first element. That means here the phosphorus greater than electron affinity than nitrogen. Here sulfur more electron affinity than oxygen. Chlorine more electron affinity than fluorine. Highest electron affinity among all the elements in the periodic table is chlorine. Right? Next, for noble gases, electron affinity considered to be 0. Why? Because they are highly stable. Next property is electronegativity. 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 So what is meant by electronegativity? The tendency of attracting capacity of electrons towards itself. The tendency of attracting capacity of electrons towards itself. Right? That is known as electronegativity. Electro means electron. Negative means attracting capacity of electron from a towards itself is known as electronegativity. Simply the tendency of attraction of electron towards itself from other atom is known as electronegativity. Here En has no units. En has no units. The highest electronegative element is highest electronegativity. Fluorine. The value is 4.0. The next or second highest electronegative element is oxygen. Its value is 3.5. 3.5. Fluorine 4.0, oxygen 3.5, nitrogen comma chlorine same En values, that is 3.0. Remember, highest electron negative element is fluorine. Second highest electronegative element is oxygen. Nitrogen and chlorine contain same En values. That means electronegative values 3.0. The En values can be measured in different types. Here, the first one is Pauling scale, measure of electronegativity. Electronegativity. Number one is measure of electronegativity. One is Pauling scale. According to Pauling scale, here based on bond energy, calculate the En values based on bond energies. Pauling scale, En values can be measured based on bond energies. According to Pauling scale, here Xa minus Xb difference equals to 0.208 root of delta. Delta is a bond polarity. Here it is kilocalorie per mole. Kilocalorie per mole. Whereas 0.1017 root of delta kilojoule per mole. Where delta is a polarity of the bond. Delta is polarity of the bond. Here Xa, Xb are the En values of A atom, En values of B atom. For a diatomic molecule, we can measure the En values based on Pauling scale. Here that equal to 0.208 under root of delta in kilocalorie per mole or 0.1017 root of delta kilojoule per mole. So hydrogen reference element, its En value is 2.1. In Pauling scale, hydrogen shows the En value 2.1. Based on the hydrogen En value, we can find the remaining other elements. So that's why hydrogen element taken as a reference electronegative value. Reference value is how much? 2.1, right? Next one is Millikan scale. Next. Next one is Millikan scale. According to Millikan scale, En value can be found based on average of ionization energy plus electron affinity by 2. Here ionization energy in electron volt per atom plus electron affinity in electron volt per atom, then divided by 5.6, you get the En value, if the ionization energy given in electron volt per atom, we can divide with 5.6. Here ionization energy in kilojoule per mole plus electron affinity in kilojoule per mole, then divide with 540. If it is ionization energy in kilocalorie per mole plus electron affinity in kilocalorie per mole, then divide with 126. Here the Pauling scale, electronegativity of Mulliken scale is equals to 2.8 times greater than 2.8 into En value of 2.8 into En values of Pauling scale, right? Millikan scale values equals to 2.8 multiplied with the Pauling scale value, right? By this method we can calculate the Millikan's En values, electronegative values, right? Next one, variation. Variation in groups, En values. Down the group, what happen? Electronegative values, atomic radius increases. That means electronegativity decreases. Left to right, electronegativity increases. Here, due to increase in size, atomic radius. Here, decrease in atomic size. Reason, electron down the group decreases, along the period increases. This is about the electronegativity. Next, electropositivity. Next, dear students, before going to electropositivity, here with the help of electronegative values of an element, we can find the nature of the bond. For example, if En difference, electronegative difference is equal to 1.9, that is covalent. Greater than 1.9 is ionic. Less than 1.9, that is here covalent 50%. Less than 1.9 covalent. 50% covalent, 50% ionic. 50% covalent and 50% ionic. If the En difference is equals to 1.9, the bond is 50% covalent, 50% ionic. If greater than 1.9, that is ionic bond. Less than 1.9, that is covalent bond. En difference is equals to, this is covalent bond, ionic bond, right? So this is a condition to know the nature of the bond, whether it is covalent or ionic, based on the En difference values. Electron difference is equal to 1.9, 50% ionic, 50% covalent, greater than 1.9 ionic bond, less than 1.9 covalent bond. Next, electropositivity. Electropositivity. The tendency of, here it is complete opposite to the electronegativity. The tendency of loss of electron. The tendency of losing capacity of electron or loss of electron is called electropositivity. From the gaseous neutral atom, the electron is loses from its valence shell. That tendency is known as electropositivity. For example, neutral atom, it loses one electron. When it loses one electron, it gains positive charge. This is gaseous neutral atom. Here monopositive ion or unipositive ion, monopositive ion. To lose one more electron, this is m plus 2. M plus 2. Here one electron, this is dipositive ion. Dipositive ion. Electropositivity means the tendency of loss of electron towards the tendency of loss of electrons is known as electropositivity. Okay. Next, see the EM difference is equal to 1.9 covalent, 50% covalent, 50% ionic, greater than 1.9 ionic bond, less than 1.9 covalent bond. Based on the EN difference, we can find the nature of the bond. Next one is electropositivity. The tendency of loss of electron is known as electropositivity. The tendency of losing capacity of electron. From the neutral atom, it loses one electron, converted as a monopositive ion. Here the monopositive ion lose one more electron, that convert as a dipositive ion. Now let us discuss the variation. Variation in groups and periods. Variation. Here electropositivity. Electropositivity down the group, what happened? Here down the group, electropositivity increases. Left to right, electropositivity decreases. Here, what is the reason? Due to increase in atomic radius. Due to increase in atomic radius. Here, decrease in atomic radius. Electropositivity down the group increases. Down the group increases. For example, lithium, sodium, potassium, rubidium, cesium. Cesium has more electropositive nature. And among all elements in the periodic table, the highest electropositive element is cesium. Highest electropositive element. Highest electropositive element is cesium. In groups, down the group electropositivity increases, along the period electropositivity decreases. Next. See students, next one is metallic and non-metallic nature. Metallic and non-metallic nature. Metallic and non-metallic nature. See the elements having less electronegativity and more electropositivity. The elements having less En and more electropositive, they have high metallic nature. Elements less En values, more electropositive values, higher metallic in nature. Down the group, metallic nature, down the group, metallic nature increases. Non-metallic nature decreases. Non-metallic nature decreases. Whereas in periods, metallic nature decreases. Along the period from left to right, metallic nature decreases, non-metallic nature increases. Non-metallic nature increases. First A, second A, highly metallic in nature. Highly metallic. Sixth A, seventh A, non-metal. Down the group, metallic nature increases, left to right, metallic nature decreases. Down the group, non-metallic nature decreases, along the period, non-metallic nature increases. That's the reason why on right side here the fluorine, chlorine, bromine, these are non-metals. Left side, alkali metals, alkaline earth metals. First year, second year, metallic in nature. Right? Some element shows the both metallic as well as non-metallic nature. They are known as semi-metals. Silicon, germanium, antimony. Right? These are semi-metals. Okay? This is about the metallic and non-metallic nature. And the liquid metal is mercury. Liquid metal is mercury. Liquid non-metal is bromine. Liquid non-metal is bromine. So this is about the periodic properties of metallic and non-metallic nature, and the remaining two properties. One is nature of oxides, diagonal relationship, and the valency. So these properties we will discuss in next session. Thank you, friends.